Well, hello everyone. In the absence of Daria, who's taking a very well-deserved vacation, it falls to me to introduce today's speaker. Although I don't think John requires introduction for most of you. John Reagan is the head of our compiler team. He's been with our company since the beginning, and he's held the same position before. John and OpenVMS go back a long time, and John and compilers go back a long time. So who better to talk about an update on our compilers than John Reagan? John?
Thank you. So yes, I recognize many names and friends on this list. As Camille said, so some background on me. I started with digital on compilers in 1983. Started on the Pascal compiler, worked my way up to multiple compilers I've worked over the years on. Well, today, of course, I work on everything, but over the years on mostly Pascal, a little bit of Bliss, parts of Gem, and then the Itanium macro compiler, and now the x86 macro compiler. So this presentation is, I started with the same talk I did at the boot camp in Boston last fall. I've added to it and updated it. I will also give the same presentation, give or take, at the upcoming boot camp in Malmo in next month. So I will be in Malmo. I'll be on display all week. Come and see me. And then if anybody here is from Berlin, I'll show up there on Friday for a week holiday. I'll be there for a week, semi-mail, and you can buy me a beer. So doing that. So let's get started. So some of this you may have seen before. I'll go through it quickly again if people are not familiar with some of our compiler history, and how we got to here to x86 today with to be honest, a much smaller compiler group. We don't have, again, not to tell stories on digital, but at one time the compiler group in digital, we had 100 people working just on compilers. Obviously, VSI does not have that. We had to do much more with fewer people. So I go a little bit of history and just kind of how we got here and how I helped move it along. Going back on Itanium and even before that on Alpha, but we had a common code generator. We still have it, called GEM. It's not an acronym. Don't ask. It's GEM. Back in the prison days, we were picking things that looked like shiny stones. So all the front ends generate intermediate code to a common interface, and then that is turned into objects per target. So where there was GEM for True64, there's GEM for MIPS Ultrix, there's GEM for Windows NT, but the front ends in general had no idea what target they were talking to. So it was really one of the first multi-target backends that I've ever worked with. And so that's where we were on Itanium. And so I said, how do I get this picture? And then on also Itanium, the C++ compiler came from Intel, so it kind of skips parts of GEM and generates objects directly. Worked with Claire back in 2014. How do I get this picture to x86? So how do I do it? What's new about x86 that we didn't know? GEM doesn't know anything about x86. Can I take that picture and move it forward? No, not really. I'll need a different code generator. And in the x86 world, there's the gorilla in the room, GCC, which comes with a horrible license, and it's a ugly, uncomfortable, mean gorilla. If you've ever been into the GCC news groups, it's not a pleasant thing. So I don't recommend that. So, but LLVM, LLVM is now a modern, comparable, up and coming backend, and there's places where there are some Linux distributions that use LLVM to build with. So Clang LLVM is just as comparable about that. There were a couple others I looked at, but what do I needed to do to get that picture to go forward? Let's pick LLVM as a code base, as a potential backend. And how do I make that picture happen? I'm going to have to convert the GEM intermediate to LLVM intermediate, and then also we're going to be using Clang as our C++ compiler, which gives me a perfectly good open source C++ modern standard compiler, which is what I've been being asked for years. Why is our C++ compiler and our C compiler a little bit behind the curve in terms of standard adoption, right? So this is kind of the picture we ended up with. I just needed to write, there's multiple of us, a converter that you can see on the thing called G to L, gem to LLVM. I was not very smart that day. I came with an acronym to convert that gem intermediate into LLVM intermediate. And on the back of an envelope, it seemed really easy, just a circle with some letters in it, and I'm done. So it lets all those existing legacy front ends still think they're talking to gem. They create gem symbol tables, they create gem intermediate language, they call gem interfaces to do command line processing. Those legacy front ends have needed almost no changes going forward. We had to, of course, come up with a macro compiler to port the operating system and the users that use macro. There's many of you out there. And then again, how do I retarget C++, which uses only LLVM, have to bootstrap it to VMS. C++ is a different story. We'll talk about that a little bit later. Right. So this is the picture I came up with. To be honest, looking back, where, I had to, it was easy from the backend envelope. What was the real problems? Well, the gem intermediate language is big, and we had to map all of that to LLVM IR. Some of them were simple. Some of them were nightmares. There was many more. There's things I just kind of hand waved and said, oh, LLVM can't be this bad in terms of describing something, let's say, that COBOL does or Bliss does. Turns out, yeah, it's quite different. I won't bore you today but the static memory initialization has haunted us for a long time on how to initialize a PSEX, or if you're a Bliss programmer, these anonymous pure literals, these plits. They're really a pain in the butt, or Fortran comment blocks or Fortran equivalences. Getting adds and subtracts done were boring. Getting the other stuff was really the challenge. There's things about VMS that are kind of unique. We have still 32-bit stack. We have a 32-bit heap. We have extra dwarf for a lot of our legacy languages that are not in, at least in the dwarf that is in the LLVM that we're using. There's libraries that do the try and catch and how to do stack walking. So all that is in there. We had to go through and touch a lot of stuff in LLVM, though if I looked at the code base and looked at the number of lines of code that we changed to the back end, we'll talk, Clang is different. We'll talk about that again later. I haven't looked lately, but out of the large number of the code base of LLVM, we've probably touched 2,000 lines, give or take, which I think percentage-wise is quite small. I'm quite happy with it, which leaves us in a great position, hopefully, as we move forward and pick up newer versions of the back end in the future. So again, early on, we had to do cross compilers to bootstrap ourselves from Itanium to x86. They were Itanium hosted. The challenge here even makes it more fun. For people who've used the Itanium C++ compiler, it's barely C++03 compatible, and I was not going to spend any time to make that compiler better just to bootstrap it. So I had to find a relatively vintage version of LLVM that just was capable of being compiled on Itanium. So that was a challenge as well, which kind of led me to not having a C++ cross compiler. There was issues of getting that to move over. So, but we essentially had to bootstrap everything, and today we have a native C++ on x86, and we're starting to use it to build itself on x86. So I think by this time we bootstrapped all the compilers natively. Okay. So that's kind of some of the backstory. We'll talk in more details in a second. If I look at, here's the current version of I think I picked these numbers off the support portal yesterday, of the current versions of all the compilers. They're all native. They're all natively built with an optimizing compiler. So the cross compilers are non-optimizing. So all of these were built with optimizing compilers and generate optimized code. Again, that has been some of the challenge that to tell the LLVM optimizer about certain unique things about Bliss in particular, or some weird stuff about COBOL that it doesn't see. There's some hidden dependencies in some of the runtime information that LLVM wanted just to optimize away, saying, you don't need that routine. It's like, yes, I do. It's called back from the RTL. Please generate code for it. So it took us a way to get here, including we do have a native assembler. If you want to use to write x86 assembly, it's actually just a component of the LLVM toolchain, LLVM-MC, which is their machine code tool. It's an assembler. It's LLVM's assembler exactly. We haven't, other than a few memory model changes. And not to be a plug for x86 systems, actually LLVM's tooling is quite impressive. It's an assembler and a disassembler all rolled together. And if you ask it right, it knows how to convert between, I'm really impressed, AMD syntax and Intel syntax. It's a lovely tool. So there's the versions we have today, including and most of these bug fixes have been minor bug fixes now. They've been relatively stable. There's a handful here and there. We're actually working a lot on improving the dwarf to getting the debug experience better. I'll talk about the debugger better in a minute. And then again, C++, where it's always different. So again, here the debugger. This is another challenge of going to x86. There's many things that recompiled in Go in the operating system. Claire could tell you other things along with other people in the operating system. But the things that the compiler toolchain had to worry about is that Gem only generated a dwarf 2, dwarf 3 subset. And that's what our debugger expected. It was, really addicted to what Gem did. It got really dependent on that. Well, LLVM generates dwarf 4 and doesn't know anything about our legacy compilers. And it was generating tags that are legal dwarf all over the place. And our debugger, not so graciously when it encountered them, didn't just like ignore them silently. It usually would scream and often just corrupt your stack. So that really would made the original debugger not very useful, including me. I spent most of my time early on debugging with Delta, not with the debugger. But now I use a symbolic debugger all the time. That's all I use. But we had to go through, teach the debugger about not just the new hardware and the new register set, but all of the new extended dwarf stuff it's never seen before. So that has been, I won't say a challenge, but has sometimes been tedious just to go through, because we have to remember our G to L picture. I had to get those legacy front ends and then G to L to convince LLVM that you know about Bliss and you know about Pascal variant records. And it's LLVM says, I don't want to do that. And that's part of that code we've had to add to LLVM. So, and so it's been a change to that. So a lot of time, anybody here waiting for better debugging for their favorite language, it's often a combination of, I need to fix the debugger, and I also need to fix the compiler, because again, if LLVM did not want to even talk about Pascal variant records, I don't care if the debugger is ready for them or not, I need a better compiler to tell the debugger about it. So it's been a two-step process. But again, the upcoming update 1 for 923 is I think much better. I think that's quite stable. And then, like I said, except for the esoteric weirdnesses, I think that and the current compilers are pretty good. I'm sure you'll tell me otherwise. One of the other things that took a lot of time for is, we saw in that picture where the legacy COBOL front end just recompiled in Go. Using G to L. The COBOL cross compiler was pretty easy for me to look back and say, but pretty straightforward. Macro, of course, is always different because macro needs to know about the target instruction sets. And the challenge we had here is that unlike on Itanium, where there's a lot of hardware registers available to the compiler, 128 of integer registers, x86 just doesn't have enough registers. I know there's now a future x86 extension that adds, doubles the register set from 16 to 32, but I can't code to that yet. So where to put all, people who are writing in macro code, and there's a handful of you here, And there's a whole bunch of macro code in the operating system, as I see a bunch of code that talks about VAX instructions and VAX alpha registered names, where to put them. And I ran out of hardware room. The only choice we ended up with is we had to invent some memory location pseudo registers. So every time you see what looks like a register 2 or 3 or 4 in your macro code, you're really talking about fancy memory locations. And so now there are memory locations that handle those alpha registers, but they now have to be managed by the operating system because they have to be saved on interrupts. They have to be context swapped. They have to be moved around. They're not just per process, they're per thread. There's many issues going on to track this. So there's not just one set of alpha pseudo registers, there's an infinite number all floating around the system at the same time. But we had to deal with all that. So, people who used to write macro 32 code thinking you're going to get the tightest possible code on the planet. Macro 32 on alpha, and I Titanium in many cases generated some really good code. You'll look at on x86 and there's reads and writes to memory all the time. And what I want to do is say we're saved by cache. Every other Linux or Windows system on the planet that uses x86 also has to live with the same limited hardware register set. And they also have variables on the stack all over the place. They read and write the stack all the time. Well, they work fast because the stack ends up living in cache. And then these alpha pseudo registers, as we've seen, I've done a little bit of study, they end up living in the cache. Of course, until your process gets swapped, but no different on Linux. You change processes, your stack is different location and the cache has to flush and refill, right? And so there's a lot of places where we had to deal with macro and linkages and hardware registers. But in general, I think at this point, the code that's there, if you have existing macro 32 code, I now think it's recompile and go. Other than the fact that the compiler needed a lot of work. Right. So there's that. So the non-legacy, the legacy compilers, again, as I said, were in fact pretty well written. They compiled quite easily. Again, like I always pat myself on the back, once I got to making the first Pascal cross compiler took me an afternoon. It was not difficult at all. Again, things that we've bumped into, I've talked about, again, static data initialization comment blocks earlier. Obviously, code that knows about hardware information. Well, we talked about the debugger, but anything of yours, if you had condition handlers, if you have code that looks inside of an object file, we still use ELF on and dwarf on x86, but the relocations are different. So if you are having your own tool that does that, I don't know why, but that's where we had to make changes to analyze object, analyze image. Obviously, the linker needed substantial changes. We'll see in a minute, we even had to make changes to the librarian, not for the legacy compilers, but for C++. C++'s use of long names and mixed case and VMS weak versus Unix weak symbols. We've had to, behind the scenes, extend a handful of those compiler toolchain programs as well. One of the things people have asked even early on is, like, anytime you change architectures, what bugs will be uncovered? Whether it's VAX to alpha, alpha to titanium, every time we did it, we find a bug that you look at and saying, how can this have been here so long? And we have found the same thing again, and I'm sure customers of you have found the same thing as well. So the ones that probably were the highest ones we've seen is gem on alpha in particular. If you had an integer, a 32-bit integer, and you have it as a local variable, going to go on the stack, fine. Gem would always put it in its own quad word, because getting quad word granularity, alpha really liked to read and write quad words. It would read and write long words, but even to be honest, read and write quad words were faster than read and write long words, and anything smaller than the 32-bit If you had them next to each other, you have to kind of carefully grab them, pull them apart, and put them back, but make sure that no one's touching the 16-bit word next to you. It was a nightmare. So Gem just put them all in their own quad words, which was great. Is alpha. You had memory, the stack is fine. But then what happened is that we had a handful of code, some Bliss, some C, that there was a 32-bit variable allocated on the stack. Gem allocated some extra alignment padding next to it just to be for performance. And then the code wrote 64 bits to that 32-bit variable. And so on our lovely little-ended machine, the extra memory that was written was the alignment hole. No one noticed, no one cared. Your 32-bit variable could have been treated as a 64-bit variable. And if you're really unlucky, your program worked. Declare a 32-bit integer variable, then read and write the 64 bits to it all the time. You might get lucky. Not so with LLVM. LLVM says, there's no performance benefit on x86 for such alignment holes. We didn't code that into G to L. We said we wanted, if we're going to go to x86 for VMS, I'm trying to get the best performance that I can. So we didn't code any of that stuff in. The hardware was fine. We did some performance tests, and read and writing bytes versus words versus long words, the performance was the same. The cache saved you, right? Again, I've reminded a lot of people, Intel charges, if you look at the costs of their chips, the expensive ones are not the fast ones. The expensive ones are the ones with the most cache, right? They charge by the cache line, not by the clock cycle. The other big change that we did for x86 is we've by default moved code out of 32-bit space into 64-bit space. Part of the reason for that is that it leaves more room for your 32-bit stack to grow. It leaves more room for your 32-bit heap to grow. And so move it out there. Itanium does have some latent support for putting code in 64-bit space, but the default there is always still 32-bit space. We changed the default. So code, unless you ask otherwise, and you can get it back the old way, will go into 64-bit space. So there were some assumptions if you have in code about that, except now we made that change, and it's like, well, John, what about all the places that assume that pointers to routines are 32 bits? They're everywhere. They're, just the same way that data descriptors have 32-bit pointers in them. That's why we still have to leave variables on a 32-bit stack. We still have to leave static data in a 32-bit address space. By the way, a side thing, early on, we did look at, could we move the stack to 64-bit address space? We looked at that for about an hour until we realized that there's no way to do that. So, well, no easy way that wouldn't change every macro program on the planet. But there's a lot of people that, that have these assumptions of 32, 64. What happens on x86, if you look carefully at a link map, you'll see that the linker now generates a whole bunch of trampoline routines. When you get the address of any routine, you get back a 32-bit address. What you get back is the address of essentially a 2-instruction trampoline, which bounces you to a 64-bit address. But you can still pass that around. You can call it. It works just fine. But the linker manages those. So there's all these, that's what a routine value is. And then, as some of you know, including Brian recently, inside of symbol vectors and execlets, what used to be these, address data pairs in symbol vectors, a symbol vector now feels way more like a VAX did. A symbol vector in a shareable image is now just an array of routines, little trampoline routines that bounce you from 32-bit space to 64-bit space. But we had a few people that we found some code, mostly in Bliss, some in C, that got caught by that. So we fixed that. I don't know if anybody else has seen that or not. And then the one that is, again, popping up more recently is the LLVM optimizer in many places does much better than Gem does. Again, for a machine that has so few registers, it works extra hard to find things that it doesn't have to store or use a register for. It has one of the things we've seen so far is if there is a variable that is not initialized at its declaration, and let's say you have a code, you have an assignment statement that initializes it in the then part of an if, but not in the else part. LLVM says there's a possible code path to get from here to some use of this variable that you might end up with something that's uninitialized. Now you, the human, looks at that and saying, I have enough logic in my program. It's never going to happen. It can't go through the else the first time around the loop. It's got to go through the then the first time because my check of my if checks something. I don't know. We've code that has worked just fine for years, worked fine on Alpha, Itanium, might even work fine on VAX. That LLVM says, I see a potential code path that might be uninitialized. So therefore, this program really has an undefined behavior because one out of a million code paths will get you an undefined value. Thank you for doing that. And there are LLVM sanitizers that can help you flag them, and I'll talk about them in a few minutes. But LLVM just is great. This program's invalid. And like we've always joked, I mean, what do language standards require from invalid programs? They don't say. So we found one case where LLVM says, if one path is invalid, all paths are invalid. So it went to every use of the variable and it just replaced it with a 0. It's like, oh, so we found it quickly. Trust me, when you start fetching, we have several programs that just stopped working. It's like, why? Because we tracked it back, found the uninitialized variable, initialized it either at the declaration or in the else part, and then it works fine again. But so the more aggressive optimizer can uncover broken programs. But working one's fine. And again, I really haven't going to talk much about performance other than we've done some early studies from it. Again, as I mentioned, the LLVM optimizer does a really good job. And to be honest, x86, love it or hate it as an architecture, is in many places better than what we had to deal with for Itanium. A gem on Itanium used about, if I had to guess, half of what the architecture provided. You can argue whether any implementation ever lived up to the architecture's, hopefulness. But the lack of an integer multiply on Itanium has always been a challenge. Though recent ones have it, but Gem doesn't know about it. So, you want to do some integer multiply as part of just an array indexing operation. We had to use the floating instructions to do integer multiply. It was a nightmare. So you get to x86, one, it has an integer multiply, and two, it has much nicer addressing modes. So anything like array indexing is just buried in an addressing mode. And we've seen programs that, again, apples and oranges, you can compare clock cycles and whatever, but, that take a minute and a half on an Itanium that take 10 seconds on an x86. And it's partly due to the fact that Gem didn't take full advantage of the machine, but the machine forced Gem into doing a lot of code that is slow. So that's part of the we haven't done much more than that. And again, I'm not really here to talk much about the operating system, except the version you're running is still built with cross compilers, not native compilers. I'll talk about that's all I'll say today. So that's kind of where you get for legacy compilers. I'll probably, before I'll go past that, the one that haunted us the most, anybody out there who's a basic user, my apologies, basic took forever. We had no basic cross compiler. You looked at that early picture and say, John, all those compilers use Gem. Why wouldn't the basic compiler be easy to be a cross compiler? You did it for COBOL 410 Pascal. And the answer is basic cheats all over the place. The basic interface between the generate code and the RTL is, to be honest, one of the most obscure, obtuse interfaces I've seen in my career. And the basic front end also cheats on gem. I had no idea. I'd never worked on the basic front end. As we're porting things along, we're doing the other cross compilers, and I was just as naive as some of you. It's like, what's wrong with basic? Build it. And so we compiled the basic front end, and we put its gem intermediate through that G to L tool. Oh my goodness, we passed like 3% of the basic test system. Horrible. And so we had to find all the places where we implemented G to L using the gem specifications. Well, basic cheated. It looked behind the curtain, and it was filling in fields that the gem spec said back end only, don't touch this field if you're a front end. And the basic front end filled them in knowing that it can trick gem on alpha and Itanium to doing something it didn't want to do. It was, I won't say basic as the malware of compilers, but it was close. It was really tricking gem into doing something it didn't want to do. So we, of course, had to partly change the basic front end, but in my goal of being, bug for bug or feature compatible, we had to extend G to L to let it be just as hackable by the basic front end. So that's how we got to basic and why it's so slow. Or so late, rather. Okay. Back to C++. I had several customers saying I had C++ issues on Itanium. It's only C++ 03. I have much newer C++ code bases I want to bring over, including us, OpenJDK. It's like C++ 03 didn't cut it. What could I do? Could I extend the front end we have now? I don't want to get into the C++ front end business. Plus, we didn't have a license to do that. The standard template library is old. Why? I should just be a lemming and get in line and use one of the two, C++ compilers that are in the industry, essentially Clang or GCC. And since we're using LLVM for the back end, Clang for the front end was the obvious choice. Even Intel's C++ compiler, they've stopped using their x86 backend, and I think they have rehosted that to using LLVM as a backend. So easy enough said to do. Take that compiler, I can build it, except boy, does it look different than any C++ compiler you've seen on other VMS systems, right? Some things we've had to add. Some things we said, look, for years I have been beaten up on why is long on VMS 32 bits? Why is size T 32 bits? And the answer is we have code all over the place that declared these things and wants 64-bit pointers. People want 64-bit pointers by default. That's what I keep hearing over and over. Of course, the other side of my head here is people like, but I got code that's been living on alpha and Itanium for years. I just want to recompile and go. This isn't new C++ code. This isn't some new open source thing I'm bringing over to VMS. This is code that I just want to recompile it and go. Leave me alone. So we kind of split the difference. I did not want to turn Clang into a exact duplicate of the Itanium C++ compiler. It's like, let go of the past, let go of the tree, don't be a tree hugger. Like I said, I've started in '83, but I think I've learned to grow over the years. I think I can accept some new things. So we've said for well-written open source code that comes to VMS, they don't care. 64-bit pointers, they live on that all the time on a Linux box. Why not? So we've left, all those sizes are 64 bits. The very first compiler we did for Clang, we've left it at 64-bit pointers with no way of getting 32-bit pointers. That lasted for about 2 days until I introduced the C++ team to VMS descriptors. It's like, ooh, I need 32-bit pointers in those things as well. So, we do have we've added support for all those pragmas that you see on Itanium for picking pointer sizes, but the default is 64, not 32. We've left names being mixed case as is, and no length limit 2,000 character names to the linker, go ahead. The linker doesn't care. The linker really doesn't care how long a name is. It might get upset after 64K, but in general, the linker doesn't care. The linker doesn't care how many p6 you have. Thousands of them, hundreds of thousands of them. You got enough memory, the linker will chew through them all, right? So we went through, but we added a lot of stuff to Clang to make it be VMS-y. Some things we still didn't do. We did not build any VAX floating support into the compiler. If you're a VAX float user with C++ on Itanium, one, please stop doing that. But if you have to, we really don't have a good solution for that now on x86. Though I do believe that with again a couple adult beverages, you probably could write a C++ class library that can come close. But and then we also provide the compiler in two forms. We actually provided a DCL interface to Clang, which is a Linux reference compiler. We added a DCL interface on top of it, which is most of the one you see on Itanium. There's some qualifiers that just didn't make sense that were legacy ones we've just left off. But if you're a Clang user on Linux and you said, John, Clang is cool, there are over 500 command line options on Clang. Sadly, yes, there are. There are command line options I've never heard of before, and it's like I wasn't gonna invent. That all that functionality is there. I want to leave it there. If somebody wants to use it, I'm not testing it, but there is the compiler with its traditional Linux interface, defined as a DCL foreign command. Use MCR. And give it a Linux command line. It has everything you'd expect everything that's on Clang on Linux is there in the compiler. I don't know if everything's there in the headers. I don't know if everything's there in the runtime libraries. But you can turn all that stuff on. Again, for C++, I think you're not going to get all of, like, if you have something from C++ 17 or something, which the compiler supports, it's a Clang 10 compiler, but it still supports all of those things. I don't know if the RTLs have all the coverage yet or not, but it's there if you want to try to use it. The other benefit is that you can, and again, I'm technically not supported today, but we're looking at this as how do it's the Clang compiler is it's actually multiple compilers in one. Clang can be a C++ compiler. It can also be a C compiler. And one of the other complaints I've gotten over the years is, John, your C compiler on Alpha and Itanium is C99. And that's it. Whereas I need stuff from the C11 standard or newer. And how do you get C11 on our compiler? Not on our legacy C compiler, doesn't know anything about that. Now on x86, could you ask Clang, hey, be a C compiler instead of a C++ compiler? And it will be. And it'll give you all of those C11 features in it. Now, again, we're working on that. It's a future. I think the compiler is mostly fine. It's the headers that need some work and the RTLs that need some work. If you have any C11 code that wants to use things like threading or atomic access, stuff like that, the compiler might work, but it may not link, you may be missing a header things. But if you start thinking about that, yeah, I've been thinking about it too. So where we're at now with it, and again, the naming version of this is, the v10.1. That's the 10.1 is the version of LLVM that we're using, 10.1.0. And then dash 1 was our first GA release, dash 2 is our second, dash 3 will be our third. And in the future, we're gonna bump to we'll go to a newer LLVM, and that number will go from 10.1 to something bigger. Not 11, much bigger. So let you know. One of the things we had to add to Clang, listing files. Clang doesn't have anything like that. I've gone to LLVM conferences and said, anybody think about wanting to add a listing file to your compiler, or wouldn't you want to have a written, at least on computer, description of every line that the compiler saw, all its command line options, all the error messages, all the perhaps generated code, all in one convenient file that you can use to put in an archive and look at later? And they look at me like I'm from a different planet. Nobody really ever bought into that, other than the few people standing around who used to be VMS users would say, oh yeah, that was cool. But that's about it. But we had to add that. And then all of the stuff with, we mentioned, by default 32-bit pointers versus 32. It's quite common in C++ code you're bringing from Itanium, perhaps, is you allocated a string from the heap using the standard std : string class or something, and you expect it to be in a 32-bit heap so you can grab the address of the data and put in a descriptor. Well, guess what? If that data now is in 64-bit heap, you only get half of your address, which never works. So the compiler now is smarter about when to. We will not just allocate things off the one heap. We allocate things off both heaps at the same time, which has made me lose almost the rest of my hair. The other thing was we now finally have the two runtime libraries bundled with the operating system. Early on, it was just more convenient for us to ship them with the compiler kits, which is different than every other compiler. They're now buried inside the operating system like they should have been. And then if you're coming from a 922 system, we do have a kit that kind of helps you transition over to get the right RTLs on the system on those as well. But at this point, I just strongly say, 923 and 923 update one of the places I would go, mainly for better debugger. There's been a handful of exception handling fixes and stuff like that. So 922 is, in my opinion, is something I works fine, but from a language, program development point of view, 922 shows some rough edges and some bugs. Coming up for the next kit for C++, it's some bug fixes. We're doing some minor changes, and we're getting to the point of, like I said, using our own compiler now on VMS to build our own compiler on VMS. Building C++ is a little more complicated, mainly because it uses CMake as a makefile building tool. And so we've of course had to port and move CMake over at the same time. We do internally have a version of CMake for those CMake fans out there. I do want to get a kit on the system somewhere at some point, to put on the website. The version we've ported is a little bit. CMake seems to change, is quite active, and they seem to go forward with their version numbering and new features at a pretty high rate. So the one that we ported is not the current one. Now that we've done it, I think I'm going to go back and have them do it again. We've learned it the first time. We can probably turning the crank the second time should be easier, and get a better CMake to provide that on the website. A little bit about futures. I think I kind of hinted at some of these things before. We still don't have good working long double support. Anybody who's using IEEE XFloat, whether it's RealStar 16 in Fortran, Pascal quadruple long double in C, C++, quad in BASIC, the XFloat rather. That's a difficult problem. You need both support in the compilers and support in the RTLs. The cross compilers don't support it because the older version of LLVM used in the cross compilers didn't support the 120-bit float, only 80-bit float. My brain is full of floating point these days. So we're bootstrapping our way up, but you need natively built libraries to work with the natively compiled code to get that. So that's still a work in progress. Improved optimization. The optimization that is in the compilers now with LLVM is pretty good. If I had to give a number 1 to 10, we'd probably at an 8. There's still a few pieces of internal metadata that I can give LLVM about some pointer aliasing to have it do a little better. So there may be places where, again, I talked earlier about using Clang as a C compiler, or even as a C++ compiler. It might get a little better code. If you have a piece of C code that is runnable also as a C++ code, push it through the C++ compiler. Might be a little better. I don't know. Again, we're working on the debugger support. And then I'm still struggling with machine code, right? Today, you on x86 use analyze object disassembly, and you pull it out of the object file, which gives you code, but doesn't give you static data, doesn't give you symbolizations. I'm looking at that. It's a struggle. Adding that into LLVM to teach it to generate an object file and an S file at the same time has proven to be interesting. Uh, I don't know if my C++ is capable to put another object interface over an object interface over an object interface. It's possible, but we're still looking at that. Right. We're refreshing LLVM. We're working on that now. I think we've built in links some of the pieces of the current. I think we're using 20.1.1 in the tree we have, but it's easily just to upgrade from that. Like I said, and then I mentioned earlier some of the LLVM sanitizers. LLVM has a bunch of tooling that comes with the compiler. Simple things like disassemblers or their version of obj dump or their version of dwarf dump or tools like that. But they also have some sanitizers you can, along with the least Clang, but it's mostly in the back end. You can compile and these additional sanitizers, they're kind of like little RTLs that you link in or use with your program that can find use after free or data type storage offsets, like the whole storing 64 bits into a 32-bit thing. So we're looking at that. I think the ones for LLVM 10 I don't want to bother with. I think once we get to LLVM 20, I'll pick up and look at some of the sanitizers. So when we release compilers based on LLVM 20, not sure when that will happen, but we're working on that now. I'll probably at some point want to pick up a bunch of the sanitizers as well. Right. So that's kind of the high level overview of what goes on the compiler team. As you can tell, there's a lot of things that we juggle all at the same time. We still, of course, trying to support, you'll find many of us in the support forums on the website. There's a few of us that still hang out in comp.os.vms. And you probably can guess my email address. So, I'm still here today. So send me some email, drop us a message on the support forum, or of course talk to support. They're quite capable of helping you if you have a support contract. Obviously, if you're here, you probably have one of those, or you should get one. Keep me employed. So that's kind of where I want to stop for today. Here we are running 10 minutes up to the hour or so. If there's any Q&As that we want to start and go into, and we can work from that.
Thank you, John. Yes, so if you have any questions that you'd like John to answer right now, then you can put that in the Q&A box. And actually, one question came in while John was talking. Question is there any plan to add a cc/clang option or something similar to compile C files with Clang without needing to use the Linux-style command?
Yes, there is. As a matter of fact, today, there is a /clang qualifier on CXX. It's in the help file. And you can essentially, it's a way to force Linuxy options through the DCL interface. And you would say, matter of fact, I used it just today. I can give you the details or I can post somewhere on the forum. But yes, you can, it'd have to say Clang equals what paren quote -x quote comma quote C. It's a little more arcane, but to be honest, isn't that the fun of Linux command lines?
Right.
To be arcane as possible. Yeah, we have that today. And using that in this Clang qualifier, you can force any one of those 500 options and ask Clang to generate code or run some optimization phase that we don't do. And good luck to you. Tell me if it works.
All right, next question. Why does macro have problems with labels and psects with the same name?
That's an LLVM issue, and I think we've worked around that. LLVM's belief, because they inherited this behavior from GCC's gas assembler, is that when you use inside of an assembly file, if you're going to write a real x86 assembly file, that labels and section names are in the same namespace. And if you have a psect and a label, they conflict. Now, I have argued if somebody wants to go to the LLVM discourse website and read all and participate in LLVM discourses, I argued this hard that I said, if you read the ABI and the ELF spec, names of sections and names of symbols have two namespaces. They have since resisted to do that, but yeah, that's why as an LLVM, I believe bug, they claim feature. But I think we've worked around
it. Next question, and there's actually two versions of the same question being asked. Would it be much of an effort to provide the OpenVMS LLVM interface as a shared image or as a library?
Certainly as a library, I think it's reasonable to provide any of that. I think, certainly given the licensing that is the LLVM license, there's nothing that precludes us from providing all those changes we've made. It's just up to us. I mean, we have not checked it into the official LLVM repository at LLVM 10. Once we go to 20, my goal, I have no idea how well this will work. I want to get a real VMS triple for LLVM that at some point you'd be able to hopefully download LLVM, maybe from llvm.org or at least from us, and build it yourself if you want to. That's why we're trying to build it natively on VMS with our own compiler. I'd like to get to the point to let you build your own backend and then hook whatever front end you want to it.
All right. Next question. When might we be able to see a more recent version of Fortran, maybe using Flang?
So I actually watch Flang. It's one of the Slack channels I follow as well. To be honest, if you want my opinion, they're not making as much progress as I thought they would. I mean, they started with their very first Flang version 1 was this older C compiler that they hacked up to use LLVM. They're re-implementing Flang as a newer compiler. It's better, but the last time I saw is that Flang 2, which is now part of the LLVM 20 distribution tree. So one of the reasons we're switching to LLVM 20, if we pull the whole tree down, we'll get the entire Flang 2 code base. I still thought it generates C code as an intermediate. It's a Fortran to C converter today. Doesn't generate LLVM, doesn't give you objects. You have to use you have to use Clang as a C compiler to do that. So it's on my list. It's on the vision. I don't know when that will happen.
All right, thank you. Local labels in macro don't seem to exist when running the code in the symbolic debugger. I've had to change such labels to global labels. When will this be fixed? And also, when will I be able to enter examine/condition R0 in the debugger?
So, the local label thing I kind of know about, and that's we have to that's on the list. I would have thought examine/condition R0 would have worked. I mean, the debugger does know about those alpha pseudo registers. So when you do an examine R0, it knows how to go find those alpha pseudo registers for the frame that, the scope that you're in to find them. Maybe it's fetching it from the wrong place, or maybe, I don't know. That's a good question. I'll write that down.
Right, we can look into that. Are there any plans?
That's the first thing I've heard of that.
Okay. Are there any plans to port Rust or other modern languages which are also based on LLVM?
I would like to do that. I think I've talked. I don't. There's nothing in a roadmap. There's no talk about, but it's quite possible.
Okay.
Anybody want to volunteer? Rust is open source. You want to jump into the Rust community? Come talk to me in Momo.
Right, and I guess that everyone who is interested in using the LLVM tool chain, just contact us and we can figure out what we can do.
I think that given that we're using LLVM now, you have a big playing field. If somebody wants to deal with Rust, or I'm not sure if putting Swift on VMS has any use to it, but you can imagine Rust or Go as being two potentials, right?
All right. Thanks, Jan. I think we've come to the end of our questions. So thanks everyone for attending, and thank you, John, for presenting.
Okay, like I said, you all can find me. You know, either can guess my email address, the john.reagan@VMS Software, or just ask questions on the website forum. I go there about every day just to look.
All right. Bye, everyone.
Okay. Thank you.